Limits of a sequence, example 1. Evaluate the limit as n approaches infinity of 3n squared over n squared plus 5. Part 2, the limit as n approaches infinity of n cubed minus 4n over n squared minus 2. And part 3, the limit as n approaches infinity of n squared plus 4n over n to the power of 4 minus 2n to the power of 3. So part 1, I want to evaluate the limit as n approaches infinity, so as the n value gets bigger and bigger and bigger and bigger and bigger, of 3n squared over n squared plus 5. So I'm going to divide above and below by n squared. So I can do this because it doesn't change the value of the fraction, because what I do to the top, I do to the bottom, what I do to the bottom, I do to the top. So that won't change the value of the fraction. The reason I'm doing that is because I want this 5 to be in this format. Okay, so k over n to the power p is equal to 0. We know this because this was a statement that we had to learn off. It's from the previous video, part 1. So we want to get the 5 in this format. So once we have it in this format, we can say, well, if n is approaching infinity, so whatever this denominator is, this will be approaching infinity. As this gets bigger and bigger and bigger and bigger, it doesn't matter what the k and the p are, we know that we're approaching 0. So we want this 5 to be in the format of something over n to the power of p, where the n is getting bigger and bigger and bigger. So the n is approaching infinity, because ultimately then we can just say it's 0. We can just let it be equal to 0. So if we just focus on the top, so 3n squared divided by n squared, the n squareds will cancel and leave us with 3. So that 3n squared will just become 3. And then n squared divided by n squared. So n squared divided by n squared, anything divided by itself is 1. And then 5 divided by n squared is going to be 5 over n squared, which is what we want. So now we've gotten rid of everything that contains an n, and we've changed the 5 into 5 over n squared. So remember, the 5 and the 2, it does not matter what those numbers are. They can be anything at all. So they're the k and the p from our little formula, if we look back at the little formula again. So they're the k and the p. It doesn't matter what those numbers are. So long as we have something over n to the power of something, and if we're letting n approach infinity, we're letting n tend to infinity, then we know this will tend to 0. So we just let it equal to 0. So this will ultimately become 0, which is what we want. So 3n squared divided by n squared gave us 3. So that's how my new numerator is 3. N squared divided by n squared just gives us 1. So that's where that 1 is coming from. And now we have 5 divided by n squared just gives us 5 over n squared. So that's where that 5 over n squared is coming from. So notice now we've gotten rid of everything that contained an n, and the only n's left are in a denominator. And it's in that form of k over n to the power of p. So it's in that format. And the next thing we do is we just let that equal to 0. And now we have no n's left at all. We just have numbers. So we have 3, which is just a constant, just a number on its own. We have 1, which is just a constant, a number on its own. And we know that this we can just let equal to 0. Because as n is tending to infinity, that denominator is getting bigger and bigger and bigger and bigger and bigger. And it's going to be squared, and then it's going to be 5 divided by that massive, massive number. And we know that that's just going to tend to 0. So we can just replace now at this point 5 over n squared with 0. So we have 3 plus 1 over 0. So it's going to be 3 over 1, which is just going to be 3. So this, again, is something you just have to learn off. So the limit as n approaches infinity of 5 over n squared is equal to 0, because the bigger n gets, the closer the limit gets to 0. If you're unsure of this statement and why this makes sense and why this is equal to 0, which We know it's not exactly equal to 0, it tends to 0, but we just take for granted it's equal to 0 because the difference is so small. Then look back at the previous video, part 1. But this is a statement that you need to learn off by heart. Now the 5 and the 2, those numbers don't matter. It does not matter what they are. They're k and p in our little formula. So this is our little formula again. Our little statement that you need to learn off. So the k and the p, it doesn't matter what numbers they are, because whatever they are, you're still going to end up getting 0 as your output, or you're tending to 0. Okay, so then 3 over 1 plus 0 is just 3. So the limit of this sequence as n approaches infinity is 3. So we get closer and closer and closer to 0, but it doesn't actually become 0, but we take for granted that it does, and we end up getting 3 as our output. Okay, so part 2 will be done in the same way. So the limit as n approaches infinity of n cubed minus 4n over n squared minus 2. So we want to get rid of all the parts that contain n's, and the way that we can do that is by dividing by the highest power of n. And then the 2, we want to end up in the form of k over n to the power p, so that we can ultimately let it equal to 0. Okay, so we're going to divide by the highest power of n, so 3 is the highest power of n. So it'll be everything on the top of the fraction divided by n cubed, and everything on the bottom of the fraction divided by n cubed. So what we do to the top, we do to the bottom. So n cubed divided by n cubed. So n cubed over n cubed will just give us 1. Anything divided by itself is 1. And minus 4n divided by n cubed will give us minus 4n over n cubed, which is going to be minus 4 over n squared. So an n will cancel on the top and the bottom. Then dividing the denominator. So n squared divided by n cubed, again, you're dividing by the highest power of n, will end up giving us 1 over n. And then minus 2 divided by n cubed will give us minus 2 over n cubed, which just stays the same. So minus 2 over n cubed, there's nothing to cancel there. So notice now that we either got rid of any n's that we had, or we got any other values that had n's in them to let the n's be in the denominator. So that's really, really important that the n goes into the denominator, okay? Because that's why we can use our rule and let k over n to the power p equal to 0. That's why we can use our rule. So our numerator is now 1 minus 4 over n squared. That's our new numerator. And our denominator is now 1 over n minus 2 over n cubed. So that's our new denominator. So notice now we have constants. So we have a 1, or any other term has the n in the denominator. So that's what's really, really important. So we started off with n, for example here, n cubed, and that ended up becoming 1, so it became a constant. And then the minus 4n became minus 4 over n squared, so the n is now in the denominator. The n squared became 1 over n, so the n is in the denominator. And the minus 2 became minus 2 over n cubed. So again, the n is in the denominator. And that's what we want, because now we can apply our rule. So each of these are going to tend to 0, and the 1 will just stay as 1. So again, 4 over n squared tends to 0, because the limit as n approaches infinity of 4 over n squared is equal to 0, because the bigger n gets, the closer the limit gets to 0. And the same goes for the 1 over n and the minus 2 over n cubed. So likewise, 1 over n and 2 over n cubed, they also tend to 0. So we end up getting 1 over 0, which is equal to infinity. So you can't divide by 0, so you just get an output of infinity. I.e., there is no limit. And sometimes that can happen. Sometimes there is no limit. And then part 3, the limit as n approaches infinity of n squared plus 4n over n to the power 4 minus 2n cubed. So we are going to divide by the highest power of n, which this time is 4. So we're going to divide the top and the bottom by n to the power of 4. And the goal here is to make every value have the n in their denominator, or else to just change it into a constant. So we don't want n squared anymore. We want something over n to the power of something. So the n has to go into the denominator. And otherwise we just want to have a constant. Okay, so everything inside of our fraction has to be another fraction with n in the denominator. Otherwise it has to be a constant. So a number on its own without an n. So dividing by the highest power of n, dividing by n to the power of 4. So n squared divided by n to the power of 4 gives us 1 over n squared plus 4 over n cubed. And just to note, there's a mistake on page 348 in your book in the solution. This is what it should be. Just if you're going by the book, just be careful. There is some mistakes. So n squared over n to the power of 4 gives us 1 over n squared. And 4n over n to the power of 4 gives us 4 over n cubed. And then the denominator, n to the power of 4 divided by n to the power of 4 is just 1. Anything divided by itself is 1, so we get a constant. And then minus 2 over n cubed over n to the power of 4 is going to simplify to minus 2 over n. So this is our new numerator. So 1 over n squared plus 4 over n cubed. And this is our new denominator. So 1 minus 2 over n. So notice now that we have a constant, we have 1, and that all the other terms, they have the n in the denominator. So that's really, really important. And I know here we have minus 2 over n, but that's really n to the power of 1. Okay, so that will still work. That will still tend to 0. So again, they will all tend to 0 except for the 1. The constant will just stay the same. So the limit of a constant is just equal to the constant itself. That's one of the rules that we had to learn off from the previous video. So the limit as n approaches infinity of 4 over n cubed is equal to 0 because the bigger n gets, the closer and closer the limit gets to 0. Likewise, 1 over n squared and 2 over n also tend to 0. So just again to just go over those rules. So these are rules that you do need to learn off, and we will be revisiting them in calculus. But the limit as n approaches infinity of a constant is just equal to that constant. So the limit of a constant c is c. So then we have our addition rule. So the limit as n approaches infinity of tn plus Rn is equal to the limit as n approaches infinity of tn plus the limit of as n approaches infinity of Rn. So it just breaks up into two separate limits that you add. So the limit of a sum is the sum of the limits. And then the limit as n approaches infinity of tn multiplied by Rn is equal to the limit as n approaches infinity of tn multiplied by the limit as n approaches infinity of Rn. So the multiply just it stays as multiply, but we just break it up into two separate limits. So the limit of a product is the product of the limits. And then the same goes for dividing. So the limit as n approaches infinity of tn over Rn is equal to the limit as n approaches infinity of tn divided by the limit as n approaches infinity of Rn. So the limit of a quotient is the quotient of the limits. And the most important thing to learn is this statement here in red, that the limit as n approaches infinity of k over n to the power p is equal to 0. So the bigger n gets, the closer the limit gets to 0. So the k and the p don't matter. And if you don't need to necessarily learn off the letter k and the letter p. Something divided by n to the power of something is equal to 0. It doesn't matter what the k and the p are, so long as the n is in the denominator. If the n is in the denominator and we're letting n tend to infinity, then ultimately that limit will tend to 0. Now remember, it never actually gets to 0. It just gets closer and closer and closer and closer and closer to 0. But because the difference between it and 0 is so small, we just take for granted that it is 0. And we let it equal to 0 when we're doing our calculations.